Well, for me, actually, this is a very exciting topic because this is my personal best guess as what I would run on a quantum computer, I don't know, in 5 years. And, well, you can disagree with me, but I try to convince you of it. It's a good candidate for that. And this is joint work with Anthony Chan, Michael Castoriano, and Fernando Brandao. And yeah, so we looked into this question, how to prepare thermal states on a quantum computer. It's also known as quantum metropolis sampling. So one way to ask what we do here is quantum thermal state preparation, which is you immediately bumped into this hardness result that this is a QMA hard problem, so you probably shouldn't try it, because if you are just given a quantum Hamiltonian and a quantum computer, then preparing the thermal state is actually QMA hard. And so what it means is that you have this Hamiltonian, you diagonalize it in, so these are the eigen states of the Hamiltonian and the corresponding energies, and you want to get a mixed state with these prefactors and the quantum state proportional to this. So if you define this problem like this, then this is QMA complete. You can go home and we can have the poster session because it's not very likely in 5 years. However, if you ask a physicist, then probably we reply, well, this should be a very easy problem. Just put your system in the fridge, wait a little bit, and then you are done. So what's the difficulty? And so if you phrase this problem in a different way, and you say that, well, just simulate cooling, well, that should be a polynomial time problem, because we expect that quantum computers are generic purpose devices for doing quantum simulations, so this should be just as good at it as Hamiltonian simulation. And, well, if your system is like most systems where this conventional wisdom applies, that this thermalizes quickly, then just simulating this thermalization process, you should quickly get your Gibbs sample. And this also connects to other famous problems, such as the ground state preparation problem, which is an issue in, for example, quantum chemistry type simulations, where people often assume that you can just start with the ground state of your system or find some state with high overlap, but it's not so clear how to get this done in general. And one alternative would be to do this thermal state preparation with very low temperature, which should have high overlap with the ground state. Okay, so hopefully this gives motivation to this problem. And so now I would like to quickly go through the main approach that we follow. And this follows a line of research that was mainly started by Tema et al. A bit more than 10 years ago. And so they had this paper called Quantum Metropolis Sampling. And there they combined two powerful ideas or topics. And one is this classical Monte-Carlo sampling, which is a very common algorithm in practice. You can try some classical physics simulation like Ising models. It's also used for optimization problems, constraint satisfaction problems, machine learning. So this is a very successful paradigm in classical computing, which is used a lot in practice. And then connect this with the theory of open quantum systems, the theory of thermalization, thermodynamics, and quantum chaos. These are some keywords in this area. And you put these two successful branches of computer science and physics together, and then you are expected to get some interesting quantum algorithm. And there were some interest in this problem initially, but then there was like a few years break when people looked at different kind of problems, but recently the interest re-emerged. So the early algorithm by Tema was followed by a suggestion of Jung and Aspuru-Guzik, who further improved these quantum thermal simulations by quantum walk techniques, giving an optional quadratic speedup. And then there was 2 years ago by Wozniak Tema, they showed some further connections to some nice physical master equations, and some assumptions were removed very recently by Ra, Wang, and Wozniak. And so if you look at this line of research, then you probably expect that, okay, well, this is probably solved pretty much, so why are I'm talking about this once again? And so the difficulty is that somehow I will tell more about this, but in some sense, in the quantum case, you have a hard time figuring out the energy levels of your system, and you can only figure that out approximately. And this is a major technical difficulty because all the classical analysis just assumes that you know the energies perfectly, and that's impossible in the quantum case. And then there were various fixes for these problems. Maybe you can assume a perfect phase estimation. That's basically just saying, okay, I ignore this problem. And then there was some rounding assumption, which basically assumed that certain periodic gaps appear in your spectrum, which is absolutely unphysical, but under this assumption, you can prove that this algorithm works. And then in this last paper, they showed that basically you can remove these unphysical assumptions, but then that works with some, like, basically they force this rounding on the Hamiltonian artificially, and that also leads to an algorithm which is kind of complicated and also very far away from the physical origins of this problem. So we wanted to simulate nature and get a natural quantum algorithm. And before I can explain you how our quantum algorithm simulates nature and what is exactly this master equation that pops up, I would like to explain the classical counterpart of this method, which is Markov chain Monte-Carlo, because conceptually it's much simpler, and then the formulas that will appear will hopefully be less frightening than if I would just start with them right away. Okay, so in Markov chain Monte-Carlo, you want to implement a Markov chain where you know that it converges to the correct distribution, the Gibbs sample, this thermal state that you want to prepare. And so how it's usually achieved is that you design transition weights between states so that they satisfy this so-called detailed balance. And that means that if you have some state S1 and S2, then the ratio of the probabilities of the transitions from S1 to S2 and S2 to S1, that is proportional to the energy difference, more precisely the exponential of the energy difference of the two states. For example, in metropolis sampling, basically if the energy decreases by one move, then you always accept it, and when it goes up, then you accept it only with exponentially small probability in terms of the energy difference, how much it would raise the temperature, sort of, the energy. Okay, so this is a very nice tool in the analysis, and if you have this detailed balance condition, then it ensures that the stationary state of your Markov chain is exactly the Gibbs state that you want to sample from. And so how it is done, usually that you just start with a process which is some walk, and at every walk step, as opposed to just blindly applying the walk step, you also examine how much your energy changes, and then maybe you retract a step. And this is how you can construct such a chain. So these arrows, these blue ones, show you that the energy is decreasing. It's like cooling, and the red ones are that energy is increasing, so it's like warming up. And then so you are less likely to warm up than cool down, and then this is how somehow thermalizes to the final state that you want. Okay, so a little bit more details about this algorithm. So you have still the classical case. You have the Hamiltonian, which is just defining your energy levels, and can be a classical Hamiltonian, just diagonalizable. You have some inverse temperature, and then you have some set of jump operators. Well, in the case when you work with an Ising model, then this is simple, just coupling between two neighboring classical bits. And you can choose your jump operators as a random site and flip a random bit to its minus version. That would be spin flips. So that would be the original process that you start with. And then to make sure that you converge to the right distribution, you are modifying this walk that, as I told you, if you are decreasing the energy in the jump, then you always accept that move. And if this bit flip, which was just a random bit being flipped, if that would increase the energy, then with exponentially small probability you accept the move. Otherwise, you reject it and just go back to the previous configuration. So this is now a modified walk step, and because this will satisfy detailed balance, it converges to the right distribution. And so in this talk, I will consider continuous time Markov processes. So these are really jump rates. So what's the probability that in the next second you will make a transition? And then the original jumps are just pick a random site and do a flip. And then the jump rate is essentially decreased by this reject step. Okay. So now on the left side, you see this classical Monte-Carlo, where you have classical spins, and the probability is just this diagonal matrix, this distribution weighted by energies. And you have classical Ising models, say, and jumps are just single-site bit flips. And this is the metropolis Hastings algorithm, which relies on detailed balance to show correctness. So in the quantum case, we would work with quantum states and prepare this Gibbs state, which is now a non-diagonal matrix in the computational basis, potentially. And you would replace your Hamiltonian, therefore, by some terms which are linear combinations of non-commuting terms, for example. And to accommodate this setting, you would maybe enrich your jump operators by allowing jumps not only in the x, but also the y and the z directions. So this is how you would generalize this classical setup to the quantum one. Now the question is how the algorithm should work and what is happening with detailed balance, and that's what we want to address here. So let's go back to nature. How is it done in nature? Well, you just put your system in the fridge, which means that you have your system, you couple it with a big bath, which has a certain temperature, and then if this coupling has the right properties, then this should thermalize and prepare you the Gibbs state. Okay, but what's the mathematical description of this thermalizing process? And this can be described in terms of so-called Liouvilleans. And so these are quantum analogs of Laplacian matrices. So if you studied continuous time Markov processes, then you know that Laplacian is this matrix which describes the infinitesimal jump rates, and you just exponentiate your jump rates, and you get a Markov transition matrix given for the current time. And now this is exactly the same thing, just doing it for quantum states, and the resulting matrices will be not Markov chain matrices, but super operators on the set of density matrices. And so these Lindblad operators are these K operators. These sort of describe the jumps. So how you jump to a next density operator. And think about this subtraction of this anti-commutator term as sort of the diagonal element of the Laplace matrix, which makes sure that you preserve the trace of your density matrix. And it turns out that this open system, open quantum system can be described by such a Liouville operator, which are the generators of this continuous time quantum channels, which you can get by exponentiating this Liouvillean and applying this super operator to the density matrix. And this gives you this semi-group structure. This is how it's called, this continuous time quantum channel. And so now this is a non-unitary evolution because your system is basically measuring your bath is measuring the system continuously. And so this can have a fixed point. It can converge to some density operator, and this is what we want to see, that it is indeed a Gibbs sample. And so the textbook description of these thermal processes is this Davis generator. And there, basically what happens is exactly the analog of the Metropolis Hastings algorithm. So the Metropolis Hastings algorithm is kind of a handmade rule for sampling from a classical Gibbs distribution. Now if you look at the textbook derivation of open quantum system dynamics, it's exactly the same thing, just ported to the language of superoperators and density matrices. So what happens is that if you have these jump operators, AA, which can be local polys, whatever, and you write this matrix in the energy basis of the Hamiltonian, and now for graphical representation, I assume that you have some linear spectral density, and the energy eigenstates are arranged by decreasing energy. Then basically, this blue off-diagonal part of the matrix describes energy transitions where your energy decreases by omega. That means cooling. Or if you look at this other off-diagonal element, that would be your energy increases by omega, so it's sort of heating. And if you are on a diagonal, that means that the energy doesn't change. And you can decompose your jump operators according to how big is the energy change along this part. And so what we learned about a metropolis Hastings algorithm, that you need to accept or reject such a jump with some probability proportional to how big the energy changes. So if your energy goes down, then you are more likely to accept the jump, whereas if it increases, then you are less likely to accept it. And this once again ensures detailed balance, and thus the Gibbs fixed point of this process. And what this means exactly that this prefactor, which is basically deciding acceptance or rejection, should satisfy that that for an energy increase versus energy decrease, the ratio should be this exponential corresponding to the inverse temperature beta. And now comes the difficulty. Here we decompose this matrix according to the exact energies. And now that would suggest that you do an energy measurement, maybe before and after the jump, and then you would need to perfectly resolve the energies to perfectly implement this rule of rejection/acceptance. And now this seems to violate the energy time uncertainty principle, that basically if you want some precision on energy, then you need to spend an inverse proportional amount of time to measure the energy. And so this is what was the problem behind all these phase estimation-based techniques for implementing these quantum metropolis sampling algorithms. And so what's the problem? The problem that this Liouville, the Davis generator, is actually derived in an unphysical way. It is in a limit which is not really a physical derivation. It's sort of taking two limits simultaneously, and that arrives at a very nice and clean formula that we have here. But this is kind of violating the energy time uncertainty, so it can't be the exact thing that happens in nature. And indeed, there is a finite time derivation of this open system dynamics, which is also called the coarse-grained master equation. And so what happens here, that now your energies will not be perfectly resolved. Previously, these A omega jumps that were just really this off-diagonal decomposition of the matrix, and that was corresponding to a Fourier transform of this form, which is maybe difficult to grasp, but it was basically a Fourier transform over an infinite interval. And now it's a finite interval, and we are still Fourier transforming. That will result in a finite precision discrimination of the energies. And this can be derived from first principles. So now the good news is that we have a master equation which is physically derived, and we have a chance of simulating it. But the problem is that the energy is now not estimated correctly, just roughly correctly. And this is a major difficulty because all previous analyses relied on this exact detailed balance. And so one of the first contributions in this paper that we show that actually this approximate energy resolution results in a Liouville which is approximately satisfying detailed balance, which then in turn approximately ensures that you have a correct fixed point. The fixed point accuracy somehow scales with inverse of this square root t, which is some interaction time-like parameter. And also goes with beta. And here, the mixing time is the mixing time of the Liouvillean, so that also makes your precision a little bit less, but only in a linear fashion. And so surprisingly, it seems that this is the first proof that actually such a physically derived Liouvillean has an approximate Gibbs fixed point in this realistic physical scenario. Okay, so this is a theoretical contribution to show that simulating this finite time version is actually meaningful because you get something approximately Gibbs state. Now we want to implement this, but we have these very complicated integrals, frightening looking, and it turns out that those integrals can be nicely represented and implemented on a quantum computer with something that is called the operator Fourier transform. And the philosophy behind is that we don't Fourier transform the quantum states like in phase estimation, but rather we are doing a Fourier transform on the operators. So this AT is defined as sandwiching the operator A between time evolution and inverse time evolution of the Hamiltonian. And if you are doing a Fourier and this naturally picks out these energy transitions in your matrix according to this off-diagonal matrix decomposition that I showed you earlier. And this you can implement on a quantum computer, which is a sort of a digital and weighted version of the infinite ideal Fourier integral, which appeared in this non-physical Liouvillean, the Davis generator. And, well, so this slide just shows you how this would be implemented on a quantum computer. And it's as you expect, somehow you need to prepare a quantum state which encodes the Fourier weights, then controlled on that you do the time evolution, then apply operator, then inverse time evolution, and then a discrete Fourier transform on this ancillary register. It turns out that this describes a very good circuit implementation of this discretization of the frightening-looking integrals in this physically motivated Liouvillean. And if you just do a little extra work, add an ancillary qubit and do some controlled rotation, and incorporate all the jumps that are possible, then this ultimate circuit is actually going to give you a block encoding of the entire Liouvillean with all the Lindblad operators. And this is a relatively simple circuit. So now you have basically access to the main building blocks of this Liouvillean evolution. Now, the last step is to put everything together and now turn the quantum representation of the Liouvillean to an actual time evolution by the Liouvillean. And so that's like the third ingredient in our paper, which is some improved Liouvillean simulation algorithms, which can efficiently use this compact representation of your Liouvillean operators, Lindblad operators. And so this is the entire circuit. This U is the T from before, which encodes a block encoding of the Lindblad operators. So the idea is that you do apply these operators, and when these operators successfully would implement some of your Lindblad operators, then condition on this success, you do a tiny rotation with angle around square root delta, and this will be indicating whether you should do a measurement or not. If you do this measurement with a small amplitude, then that's fine, that's a weak measurement. Otherwise, you are uncomputing your block encoding. It turns out that this simple circuit, if you analyze it, this approximately does a delta time step of your Liouvillean. And so if you are choosing like delta small enough and repeat it sufficiently many times, then this gives rise to scaling, which is analogous to first order Trottel scaling. So the ultimate the complexity would be something like t squared over epsilon if you want to simulate this Liouvillean evolution for time t with precision epsilon. This is the same as first order Trotter. And the nice thing here is that the quantum Zeno-like effect which appears in this weak measurement circuit actually takes care of the rejection step, which is one of the major difficulty in the early quantum metropolis sampling algorithm, which has to be handled by some complicated Marriott-Vertus type of trick, whereas here it just automatically happens by the Zeno effect. And further, we can improve this to essentially linear time and logarithmic cost in precision by the compression techniques used for this Lindblad evolution by Wang and Cleve, and everything clicks together. And so this arrives at the conclusion slide. The main result that we have, one of the main results, is that we can efficiently implement a Liouvillean whose fixed point is approximately the Gibbs state, and this Liouvillean is the one which is given by the coarse-grained master equation. The simulation complexity is also nice, up to logarithmic factors. It goes linear with the time, how long you want to simulate it, the norm, the strength of the Hamiltonian, and linear in t, which was this interaction time parameter in this coarse-grained master equation, and some log factors. So once we are done with this, we can simulate nature, and if nature nicely converges, then we can reproduce that. We can actually add a lot of extra stuff. We can start to play with this master equation and use further dampening by using some cleverly chosen Gaussian weights, which further improve scaling with beta and accuracy. And other advantage of this scheme is that it's very universal. It applies to any Hamiltonian. The only difficulty is that you need to argue about the mixing time being nice. And this does not require fine-tuning, no hyperparameter tuning. Just use your jump operators and you have the recipe what to do. And we have some further extensions. Also in this, it turns out that in this scheme we can also apply quantum walk-like techniques, which yields a Szegedi type quadratic speedup in the preparation, and also enables us to prepare purification of the Gibbs state, which is known as the thermophile double state in high energy physics. And yeah, these arguments apply to many physically Liouvillean. And one thing which is not in our paper, but we are soon going to update it, we have a different extension of detail balance condition, which actually enables us to get exact detail balance without exact phase estimation in a different way. And so stay tuned until we update it. Thank you.
Thank you very much. That was absolutely worth waiting for. Actually, I have a quick question. If the jumps are only local Paulis, those form a closed group and a finite group. It seems like if the eigenbasis of the Hamiltonian is not known, the convex hull of the states that you could arrive at by local Paulis would not include its ground state. And so you wouldn't be able to get to beta equals 0.
Well, the individual jump operators are Paulis indeed, but then these are heavily modified. So the rejection step is according to the eigenbasis of the Hamiltonian. So basically, you take this Pauli, and initially it looks nice and local, but actually, once you decide whether you want to reject or not, then you are decomposing according to these energy transitions. And that means that ultimately you are applying an operator which is potentially non-local. That is kind of bad news in some cases. But anyway, this is a very different looking operator than what you started with.
Question in the back.
Hi, thank you so much for that talk. You made a remark right at the beginning that this is what you think you'd use a quantum computer for in 5 years. Could you elaborate why you said that?
Well, this is inspired by nature. So if this physical wisdom is true that putting something in a fridge will thermalize, then probably it also thermalizes if you simulate it that way. So if this master equation is the right description, which I think we can hope that it's true, then this should, for many, many quantum systems, thermalize quickly. And well, like quantum simulation is a big topic in quantum computing. One of the early applications are expected to be related to quantum simulation. And now this seems to be a very efficient way of solving difficult problems in quantum simulation. You know, thermal states, and in some cases when thermalization happens at even low temperatures, then also preparing ground states. So this is a method which is kind of nature approved, but also now we have efficient implementation for it. And since this algorithm is basically simulating the process of thermalization, it's expected that at some moderate level of noise could be tolerated, because noise is essentially should boil down to a sort of effective temperature. So maybe you won't be able to cool down below some temperature because the hardware is noisy, but above the temperature, it probably works.
Thanks. And another small question. There was this recent work, I didn't read it, but from the title, it might be related. Do you know about the dissipative quantum eigensolver? Could you comment on whether these are related works?
Yeah, that's a very interesting paper, which I was hoping to discuss it with the author, maybe today or tomorrow. Yeah. So they are also using some weak measurement schemes, and that would be a common theme, but in a different way. So certainly we are addressing different, somewhat related problems, and therefore some of the solutions that we come up with are also related. But ultimately, I would say that the two approaches have very different flavor. But yeah, there are some common tools, that's for sure.
Thank you so much.
Yeah, so thanks for the talk. I was just wondering, so you made the analogy, right, with the classical stat-mech models. And so there we know that if you do this, these local updates, if you get close to a critical point, for example, these chains, they have a lot of rejections, and so it's very, very difficult to sample from them. So just wondering, did you think about similar problems in your algorithm? Thank you.
Yeah, certainly this should be also present here. As I started with, the problem in general is QMA hard. So this should not work in the hard instances. But yeah, I wanted to be on more optimistic side of the problem, that actual physical systems that you care about, like a molecule, are more likely to be easy in this sense. So we hope that the physically motivated examples typically avoid the hard instances. There could be, of course, cases when you run into trouble, and that's like one of the bigger questions: how can we give some upper bounds on the mixing time? And that's a very difficult problem, especially in these non-commuting systems. So there are lots of follow-up questions that needs to be answered. But if this physics wisdom is right, that just put your system in a fridge, it will thermalize, for the systems which it applies, our algorithm should also work. Now it's further research to decide which are the exact systems where this happens.
Are there any further? One more question.
Oh, I mean, you can also...
No, I was pointing at you.
Okay, thanks. That's very nice. So I actually have one of those follow-up questions. So your algorithm depends on the mixing time of this Lambda you're simulating, but let's say that you know that the Davis converges rapidly. Do you also have some sort of continuity estimate that says that whatever you're doing will also converge rapidly? Because for the Davis, we have some more tools to bound mixing times and things like that.
That's a difficult question, and we are not sure. So the problem with this Davis generator is that the unphysical nature of it is that even if you have two energies that are extremely close to each other, in principle, Davis generator can decohere them extremely quickly. And that is not physical, and also not possible in our algorithm, therefore. And so that's a difficulty. What we do show, though, is that if you are looking at this coarse-grained version, which is relative to the Davis generator but physically derived, actually the discretization very rapidly converges to that. So our algorithm runs in times and with precision that is very precisely characterized by the mixing time of this physical coarse-grained master equation. Whether, like, how that relates to the Davis generator and when can we say that they are similar, that we don't know yet.
Thanks.
Right. Thank you very much. Let's thank András one more time.